Let me start this lecture with a quote on algorithm in the context of this course. An algorithm solves a problem if it gives the correct solution on every instance. Earlier, I mentioned that we would be trying to solve several decision problems, the problem statements for which the output is a yes or no. Here are few decision problems, instances, also known as inputs, and their solutions. You might ask, why should we only study the decision problems in this course? And why not study the theory of computation behind problems like, say, multiplication? Well, with some clever rearrangement of terms, we can make the multiplication problem as a decision problem. For instance, we can draft, what's 6 multiplied by 7? It's 42. We can draft it as, is 6 multiplied by 7 equal to 42? If the machine is running the correct multiplication algorithm, it would answer yes. If you replace 42 with any other number, the answer for that problem statement would be no. So, we're covering a lot of ground in the theory of computation just by studying decision problems. Alright, I've mentioned earlier that a language is a collection of strings. Given the alphabet sigma, any subset of sigma star is basically a language. For instance, the language of strings with even length on alphabet sigma is this, which is a subset of sigma star. Alright, let us begin our journey into the theory of computation by learning about the simplest computational model called finite state machine or finite automaton. Finite automata are good models for computers with extremely limited memory, like traffic lights, household appliances, automatic doors, elevators, and many more. We shall look at the example of a coin-operated washing machine that accepts US quarters and Canadian 50 cents. For a single wash, you have to insert 4 US quarters or 2 Canadian 50 cents. If you insert more than $1, the washing machine keeps the change. At any point of time, if you insert any other type of coin, the machine enters a reject state. Once the machine enters reject state, it remains in reject state even if you put valid coins in it. You have to wait for the support person to fix the machine. Alright, let us draw a figure to visualize what is happening with this washing machine and the coins. Initially, the washing machine is ready to accept coins. We can think of it as the start state or the initial state. After the coin is inserted, the washing machine remembers whether it is a US quarter or a Canadian 50 cents or an invalid coin. Let me draw all the states that lead to a successful wash of my laundry. After receiving 4 quarters, the machine finally reaches the accept state. From then on, if you add more quarters to it, it's just gonna stay in the accept state and wait for you to start the button. Okay, so what if I insert a Canadian 50 cents at these individual stages? That's what's gonna happen. When you insert 50 cents when the total was already 75 cents, the machine is gonna keep the change, and from then on, the more coins you add, the more it's gonna take. Okay, if you add any other coin to the machine at any state, it's going to enter the rejection state. That's when the machine is broken. No matter what coin you add, it's gonna stay in that broken state. Okay, so you could insert invalid coin at any stage. Even after the machine enters the accept state, if you add a invalid coin, it's going to enter the reject state. This machine is called a deterministic finite automaton because at each state we can determine exactly which state it goes to if we know the input symbol. This lets us draw a transition table. Okay, so you look at the state and you look at the input and then write the state it would go to. So that way I'm populating the first row, which is basically at any given state, if you receive a quarter, what state would you go to? Okay, so at Q1, if I receive a quarter, I stay at Q1. At Q reject, if I receive a quarter, I stay at Q reject. Now I'm going to repeat the same thing with the Canadian 50 cents as well as the invalid coin. So once I finish this row, my state transition table is ready. Here are few observations from the state diagram. First, there is only one start state. Second, every state has transitions or arrows for all the input symbols. Alright, let us see a more abstract DFA example that operates on binary strings. Let us do a quick check if this is a valid DFA. The first thing to check is whether this DFA has a start state. There is, and there is only one, and that is important. Anyways, the next step is to check if every state has a transition for all the input symbols. Okay, so I just verified for Q0, Q1, Q3, and then for Q4, even Q4 has transition for 0 and 1. Perfect, so that is checked. I forgot to tell you, a DFA can have multiple accept states. Okay, so that's correct as well. So this is a valid DFA. Now let's see what's going to happen if we input this string to the DFA. Because the first character is 0, it's gonna loop into itself and stay at Q0. Because the next character is 1, it'll go to Q1, and the next character is 1, so it'll go to Q3. Not sure why I named it Q3, but that's fine. And because the next character is 1, it'll loop onto itself and then stay in Q3 and then eventually end up in the accept state. So this string is in the language of this DFA. Finite automata and their probabilistic counterpart Markov chains are useful tools when we are attempting to recognize patterns in data. These devices are used in speech processing and optical character recognition. Markov chains have been used to model and predict price changes in financial markets. Finite automata are used in word processors for string search and regular expression-based pattern matching. Lots of exciting applications with such simple computational models.